Hello guys, welcome to another video of in CTF, and today we are going to solve this RSA 3. So what we have here, so we have a ciphertext, we have an encrypt.py, and we have a public key, and this file is made by me and it's blank here. So let's step by step proceed that how is this key being encrypted, this flag being encrypted. So imported all, and then I get a random prime number of 512, then another random prime number 512 bits, and then multiplied them, and then the size of n, and then further is equals to 3. We make sure that the greatest common divisor of them is equals to 1, and then assert means make sure that, and we have converted the flag to bytes, and then encrypted the flag with M and E and N, and then open the ciphertext, return the ciphertext, make the public key of this file, and then exported the public key. Pretty nice and pretty clean. So we can't found any glitch here to get my prime number of for this P and Q. So what we do in most of the RSA CTFs is that we try to get P and Q, and then we proceed. So getting P and Q is sometimes a bit complex and sometimes a bit easy, but here we don't have to get P and Q. Let me tell you why. So suppose our message is small. Suppose our message is 3. So this is our message. Let me suppose our message is 3, and there is a small message, and our E, which we are going to to power it, our E is 3 here. So we've got 3. So 3, and then the N, which is a very large number, like the size of N is let me copy and paste it to decode.py. So now let me do this and then comment all of them. Okay, so the size of, firstly we've got a hint here, size, because nowhere size is used. So let's print this size. And so I print the size, and this is 1024. So it is in the length of 1024, means n is very long. So n is this much long, although this is a random one, but always n is this much long. So if our message is less than this, so n could not mod it, like n could not update it. Let me show you some examples. So 3, and then 3 to the power 3, which makes it 27, and if I take n as 100, so we will see that n cannot change the value of this, because n is greater than that. If the n is smaller than that, if the n is 10, then of course my value is being padded. But if the n is larger than that, then it won't affect my power. So if we ignore this n, the large number, we can think of this to the power this is equals to 27 directly. So let me show you once again. So 2 to suppose 3 to the power 4, so we got 81, and so on. But if we pad it, if we give a smaller n, then we'll again 81 is less than 100 and 10, and now the results are as expected, 40 and then 50, and then, so you get the point. So we have to pad it, but not with a large number. We have to pad it with small number. So the same thing is here. that they have padded with a large number, and that padding actually doesn't work because this is a very large number. So what we have to do is we have to simply cube root this message. So this is our message. So this is our message, and we have to simply cube root because E is 3. And if we are not given the E, we can easily find the E via importing this public key. But we don't want to import the public key because we have the E, and we don't need N here because N is damn too large that to pad the data. So what we have to do is we have to simply cube root the ciphertext, and we get it, and we got the flag. So this is easy, but it took me a lot of time to think of it and to search for it. So let's go below and let's import my ciphertext file. So let's open my ciphertext.txt file. Oh, sorry, and then read that, and then convert those bytes to long, and this is probably our ciphertext. So I've got my ciphertext. Let's print my ciphertext, and here we go. So ciphertext is this much, and this is, as this is smaller than the N, and this always must be smaller than N because every time we pad it, it becomes small, but this is very smaller than N. Like the N is large, N is large. So if I print the size of it, we could see that it is 861, and that N is damn too large. So N is 1024 bits of that. Okay, now what I have to do is I have to calculate the cube root of it. Now how to calculate cube root? So I am pretty new in calculating this cube root and I'm a bit new in Python probably. So what I want to do is I have thought of a process which will calculate the cube root for me if it is perfect cube. So for example, I have 556 multiplied by 556 multiplied by 556. We've got this number. So what I'll do is I'll check if the 1000 is greater than the cube root of 1000 is greater than this, and of course cube root of 1000 is greater than this. So I'll take 100. So 100 to 100 into 100, and I've got this. So now this is less than this. Now I will replace the first place of this by 2. So 200 multiplied by 200, and here we go. But this is still smaller, and I'll keep doing that. So if I'll go to 600 into 600 into 600, I'll get that this number is smaller than this number. So I'll leave it at 500 into 500 into 500. And now this number is smaller than this number, which is okay. So being smaller is okay. Now I've got the left corner digit. Now I'll move to this one, and I'll again do 510 and 520, and we'll go to 550 into 550 into 550, and here we go. So I got this, which is still smaller than this, and if I'll do 560, it will be smaller, but if I'll do 570, you get my point. So what I'm going to like 570 and 570 and 570, and this becomes greater. So I'll stick to 560 and then choose this recursively, and you get my point. So what I'm going to do is I'm going to take a random C, which is equals to some lot of zeros. Here we go, and then I'll cube root it, and I'll print that C into C into C, and let's see what happens. So this is a bit small, so I'll do it till it enlarges itself to this number, and here we go. So if I increase a 0, you can set the length increase. So I don't want to increase the length as we did here. 100 into 100, like 1000 into 1000. We don't want the 1000, we want the 100. So here we go. Now what I'll do is I'll recursively change the digits one by one. So I'll make it 200, make it 0 to 9, 0 to 9, and I'll check that if the text is greater than the ciphertext. Like if the cube of this is greater than this, then don't do anything, or else replace the word. So let me show you by doing this. So what I'm going to do is I'm going to let's for I in range 0 to the length of string, if I this C means this simply means for each value of each value in this place. So 0, 1, 2, 3, and then again what I have to do is I have to move it recursively. I have to change it recursively. So for j in range 0 to probably 10, so I'll make it 0, I'll make it 1, I'll make it 2, and move it as we wanted. And then we'll say that this may be C is equals to, we will stringify the C, and we'll take from 0 to this I, and then we'll add the stringification of J, and then we'll add the stringification of this C, and then I plus 1 to all end. So this, what this do is that if we give it let me show you what it will do. So let me comment this, and if I'll give it I and J as 23 and 4, what it will do is, let me print the C. What it will do is it will replace the 6th occurrence, the 23rd occurrence with 4, to 23rd place with 4. And then this is what we wanted. We want to recursively change the content of the places. Okay, so let's comment this and let's uncomment this. Here, oh, sorry, and here we go. So it will recursively change the places. Okay, and let's print this maybe C, and here we go. As we can see that it is recursively changing the value of the places. Now what we'll do is we'll calculate that if this maybe C multiplied by maybe C multiplied by maybe C is greater than my ciphertext. If this is greater than my ciphertext, so what it will do is it will simply break, because we don't want it break. So because we don't want it to change any of the things of my C. Like we can see that if this becomes 600, we don't want to change my C, because my C is already 500. But if it is 400, I want to change it to 400, and then 500, which is less than this, and I'll change it to 500. You get my point. So it will break, and else we'll make C is equals to maybe C, and then print my C. This probably should work, and here we go. I've got an error. So this is a string. So what I'm going to do is I'm going to convert it to int, and here we go. We've got a large list of 9s, and okay, so the problem here is with C and maybe C. Okay, so let me check it again. So what just happened is, for I in the instance, for I maybe integer of this, and then a stringify of this and this. This is maybe C, and if multiplication of maybe, okay, something is something bad is here. Let me check it. Let me uncomment this and check what is happening here. So this maybe C becomes 0. Maybe C becomes 0. Why? Okay. Integer of string. Let me remove this integer and let me comment this. Okay, this is working fine. Okay, so this is working fine till here, but if we make it integer, it breaks. So what I'll do is I'll simply wrap them all with int. So int of this. Okay, let's see what happens. So I'll simply wrap them with int of this and int of this. This should work probably, and here we go. So it solved my problem what I was trying to do, and it gave me this result. And now what I'll do is I'll print C into C into C, and I'll also print this ciphertext. And here we go. Okay, what happened is can't multiply sequence by now. Okay, so this C is actually this string, so I'm going to again convert it to int and int and int. Okay, so what we see is these both numbers are exactly the same. So we got the cube root, and the cube root is this. Let me comment this down. And the cube root is this, 7. So we got the cube root, right? Now means probably you got the message. So our message is cube root of that. So C, our message is C, integer of this. Neat. And now we'll just bytes to long, long to bytes, and then we'll give it C, and we'll print that. So we'll print this, and here we go. So simple cube root unpadded RSA, and this is what we wanted. So this was a bit easy, but it took me a lot of time to complete this, and finally, so that's it. Thank you guys for watching, and I'll see you in the next one.